Three improper integrals. Now that we have mastered the advanced techniques of L'Hopital's rule, we will use those techniques to evaluate improper integrals. The first improper integral we will look at will be what we call an infinite improper integral. And how do you identify those? Well, we have infinity or negative infinity as one of our limits of integration. Sometimes we have both of those as our limits of integration. And we call these improper integrals. So we will evaluate these by rewriting the integral as a proper integral. And then we'll be using limits. Let's take a look. So if we have our upper limit as infinity, we will introduce b and place b as our upper limit of infinity, and then we will approach infinity with b. Likewise, if we have negative infinity as our lower limit, we will introduce a, which is what we usually use for the lower limit if it's not a value, and we will place a, the lower limit, and approach negative infinity. If you happen to have both, you can see here the plan. You will place c in the middle of the integral and come up with two improper integrals, and then create two integrals with limits as noted above. Now, I want to mention our goal. Our goal in all of this with our improper integrals, in fact, let me write that right here. Our goal is, does the integral converge or diverge? That's our goal with improper integrals. Now, if an improper integral converges, how will you know it? It will converge to a finite number. If not, it will diverge if it diverges to either infinity or negative infinity. Okay, so I will kind of explain that as we get there, but that's our ultimate goal. That's why we're doing what we're doing. Let's give number 6 a try. The integral from 1 to infinity of 1 over x dx. So we notice we have an improper integral since the upper limit is infinity and it's not a constant. Okay, so let's introduce the limit, and that's the upper limit, so we'll use b. B approaches infinity, and some of your authors actually use t for all of them. And so now we will have the integral from 1 to b of 1 over x dx. And that's equal to the limit, and keep writing the limit until you integrate. So do not take the limit until you integrate. Let's write that down. After integration. Okay, and so now let's go ahead and integrate that 1 over x, that's ln, absolute value of x, from 1 to b. Keep writing the limit, and that's ln, absolute value of b, minus ln, absolute value of 1. Didn't really have to put absolute values on there, but what do we know? ln of 1 is 0. So now we're ready to go. So now we can say that we are going to plug infinity in for b. So this is actually, let me write it over here. This is actually ln of the absolute value of infinity, and that's equal to infinity. And let's remind ourselves, all calculus students must know that this is ln of x, okay? And that this point is 1, 0. So as you approach infinity, the natural log of x approaches positive infinity. So this is actually equal to infinity. Therefore, the integral diverges. Okay? Or you can say is divergent. Okay? Just trying to get you everything that you might see. Okay, let's give this a whirl. Number 7, the integral from 1 to infinity of e to the negative x dx. What do you notice? We have an improper integral. The upper limit of integration is infinity. Okay, so we'll go ahead and write that that's equal to the limit, as b approaches infinity of the integral from 1 to b of e to the negative x dx. Okay? And that's equal to, keep writing that limit, negative e to the negative x. That's the integral of e to the negative x. Evaluated from 1 to b. Keep writing that limit. Negative. And you can keep the negative out from the beginning and bring it back in. I kind of like that. So it's e to the negative b minus e to the negative 1. Just makes it easier without that negative in there. So let's simplify. Limit as b approaches infinity. And we have negative e to the negative b. So that's 1 over e to the b. And then we're going to have a plus 1 over e. Okay, this is 1 over e. Okay, so now what are we going to do? We're ready to put in infinity everywhere there's a b. So this is equal to negative 1 over e to the infinity plus 1 over e. Well, this goes to 0. 1 over huge is small. So this is just equal to 1 over e. And e is just a number. So therefore, the integral converges. We have a finite number. Okay, let's keep going. Number 8, we have a negative infinity as our lower limit of integration. So we have an improper integral. So we'll take the limit as as a approaches negative infinity of the integral from a to 0 of e to the 1/4 x dx. Now, instead of using substitution, we really need that 1/4 here. We need the derivative of the something with it in the integral. So I'm going to place a 4 here so that I don't change the problem. Okay? So that's actually equal to the limit as a approaches negative infinity of 4e to the 1/4 x evaluated from a to 0. Okay, keep writing the limit. And I'm going to keep that 4 on the outside. It's just the way I like to do it. And this would be e to the 0 minus e to the 1/4 times a. You could also put a over 4. And that's equal to the limit as a approaches negative infinity of 1 minus e to the a over 4. You write that a little bit nicer. And that's equal to, now let's put in negative infinity for a, okay? So here we have e to the a over 4. So we're going to have, we don't even have to write an equal sign there. So we have e to the negative infinity over 4. And that's 1 over e to the infinity over 4. That's 1 over e to the infinity. That's 1 over infinity, and that's 0. Kind of crazy. I can go ahead and just switch this here and just leave that, which is 1 over e to the infinity over 4, which is 1 over e to the infinity, 1 over infinity, and that's 0. So that's better than to have it right there with my work. Okay? So we actually come up with 4 times 1 minus 0, and that's equal to 4. Therefore, the integral convergent. Okay, let's go on to part 2. The second type of improper integral you're going to come across is going to be what they call a discontinuous interval or a discontinuity. Now, let's talk about this. If f has an infinite discontinuity at a or at b, or at some number c within the interval a to b, then this integral is an improper integral. And these improper integrals are evaluated by rewriting the integral as a proper integral and using limits. So basically what you need to think about is we're on some closed interval a to b, okay? And there is some number within that interval, and maybe it is, let's just go ahead and use the open interval. There is some value here where the limit of integration is within that interval, is in interval, but it's a discontinuity. So the discontinuity is a limit of integration in this interval, okay? Sometimes it's better just to teach you by showing you this, but basically, let's take a look at number 1. If you can see, this is on the endpoint, and this function is not defined at b, and we are using b as a limit of integration. We will approach b coming from the left and replace it here. Now we're using t's here because t is going to be within the interval. It's kind of nice. So basically, within the interval of a to b, so it's not necessarily an endpoint. You could still use b there if you wanted, but for a definition, it's a little tough. And then if you notice here, a is a discontinuity. B is a discontinuity. And so you will take the limit as you approach a from the right. Now, why do we even mention right and left? Well, if you notice, we are going to approach b coming from the left because b is on the right endpoint. We are going to approach a coming from the right. That's why we put the right here. If it's on the left endpoint. So let's give this a try. As you can see, we have this function f of x is equal to 1 over the cube root of x. And as you can see, x equal to 0 is not in the domain of f. And we're not going to write this every time. So we have a discontinuity at 0. It's not continuous there. And 0 is a limit of integration. So yes, you're going to have to recognize when this happens. So what are we going to do? We're going to take the limit as t approaches 0. Now let's talk about this. If we're on the interval from 0 to 1, we are going to approach 0 coming from the right. Pretend like you're standing in here, inside that integral, and walking towards that discontinuity. That's the best way to see which way you're going. So we are going to approach 0 coming from the right. And that's the integral from t to 1 of x to the negative 1/3 dx. Okay? And that's equal, again, continue to write your limits. And we're going to integrate, add 1 and divide. So if we add 1 to negative 1/3, we're going to have 2/3. And when we divide by that, we're going to have 3/2. And we're going to evaluate that from t to 1. Okay? Keep writing limit because we have not placed those values into that integrand, into that antiderivative. So I'm going to keep the 3/2 on the outside. Again, that's how I do that. And I'm going to place a 1 in there minus a t to the 2/3. Okay? And so now it's time actually to take the limit. We can take a peek at this. This is just going to be 1. And this here is 0 to the 2/3 power. And that's just going to be 0. Okay? So we're going to have 3/2 times 1 minus 0. And that's equal to 3/2. Therefore, the integral is convergent. That's a finite number. Okay, let's give this a try. Again, what do you see? 0 is not defined for this function. 1 over 0 would be undefined. So we have the limit as t approaches 0. Now let's talk about this. I think I wrote that. Yeah, I wrote that in blue. So we have, again, it's the same one. 0 to 1 coming from the right. And we're going to have x to the negative 3 from t to 1. I think that's what we did on that last one. Yeah. I wish I wouldn't have put both the same, but it's okay. So, okay. So, keep writing that limit. Add 1. And divide. So when we divide by that, we're going to have a negative 1/2. And we're going to evaluate that from t to 1. I kind of would like to have a cleanup line here. So that's the limit as t approaches 0 coming from the right of negative 1 over 2x squared evaluated from t to 1. Because this x to the negative 2 sends that x squared to the denominator. Sometimes it's nice to just have that line where you can clean it up. I'm going to keep the negative 1/2 on the outside, and I'm going to have 1 over x squared evaluated from t to 1. I guess I could have done that on the previous line. And then we have the limit as t approaches 0 coming from the right of negative 1/2, and plugging a 1 in there, we get a 1 minus 1 over t squared. Now, keep in mind that if 0 is coming from the right, this is a very small number, and it's squared, okay? So, very small positive squared, okay? So now we're going to have negative 1/2 times 1 minus infinity. And that's going to be equal to, whoops, and you need to have your infinity and negative infinity correct. Whoops, keep erasing that. And that is actually, I'm going to have to just move this. What a mess, huh? Look at this. Just have a big eraser. So this right here is a small positive squared. Okay, that gives me a little more room. And that's equal to negative 1/2 plus infinity. And of course, infinity minus 1/2 is infinity. Therefore, the integral diverges. Okay, the integral is divergent. Okay. Okay, let's go ahead and take a look at the next example. You guessed it, 27 is a discontinuity. If you placed 27 into in for x, we would have an undefined function that we were trying to integrate. So we want to definitely take a look at that. So let's write that integral, that interval here. I can maybe do it in a different color. So we're going from 0 to 27. So we are going to approach 27 coming from the left, okay? So this is equal to the limit as t approaches 27 coming from the left of the integral of 27 minus x to the negative 1/3 dx, and the limits of integration will be 0 to t now. And let's go ahead and you could think about this with u substitution, but you could also see that the derivative of the something is a negative 1. So I need a negative here so I can place a negative here. Then you have the derivative of your something. So we take the limit as t approaches 27 coming from the left. We're going to add 1 to this. So 3/3 minus 1/3 is 2/3, and then divide. And don't forget that negative that we had placed on the outside. Evaluated from 0 to t. Keep writing that limit. And I'm going to keep the negative 3/2 on the outside, and we're going to plug t in first. So we're going to have 27 minus t to the 2/3 power minus 27 minus 0 to the 2/3 power, which is just 27 to the 2/3. Keep writing limit. And we have that negative 3/2. And we're going to evaluate this in a minute. We'll actually write above that. Minus in 27 to the 2/3 power. Take a look at this. We're going to go ahead and take the cube root first, and then we'll square it. And the cube root of 27 is 3, so 3 squared is 9. So that's nice to already know that that's 9, okay? So here we go. We are going to take the limit now, so we're not going to write limit, and we're going to actually put 27 coming from the left here. So it's just, if you look up here, it's just a tad bit less than 27. So that's about 0. So this right here is 0 when we plug in 27. So we have a negative 3/2 multiplied by 0 minus 9, and we get a 27/2. Therefore, the integral is convergent. So you can say integral converges, or you can say the integral is convergent. I wanted you to hear it both ways. Okay, going on to this next problem. What do you notice this time? We have a discontinuity at 1, and 1 is within this interval that we are integrating across, okay? So I need you to know this, that we will be integrating from 0 to 1, and then also from 1 to 3. So we will be approaching 1 from the left and then also from the right. So we will create 2 improper integrals. Now, I will tell you this. You can go ahead and compute 1 integral first and see if it's convergent. If it is, then you keep going. With the other integral. If it's divergent, you don't have to do the other. Don't evaluate other integral. Because once one integral is divergent, the whole thing is divergent, okay? So, just depends on what we get, okay? So, let's go ahead and create 2 improper integrals. Create 2 improper integrals. So, we're going to take the limit as, let's create 2 proper integrals with limits. We'll take the limit, and we're going to work on this first one here first. The limit as t approaches 1 coming from the left of the integral from 0 to t. And remember, this is where our t is going to go, and this is where our t is going to go. And you can go ahead and use an s if you want, or a q if you don't want to use t twice in the same problem. It's okay if you do. And let's keep going. So this is x minus 1 to the negative 2/3 power dx plus the limit as t approaches 1 coming from the right this time. And this is the integral from t to 3 of x minus 1 to the negative 2/3 dx. Now, what I was saying over here is you can go ahead and compute this one and wait on this one, but I'll show you just working both of them together just in case. So we have this, and we have the limit as t approaches 1 coming from the left. The derivative of the something is 1, so we don't even need substitution. We can just add 1, and that would be 1/3, and divide, which would be a 3, evaluated from 0 to t, and then we'll do the same thing. And the nice thing is that our antiderivative is the same, 3 times x minus 1 to the 1/3, this time from t to 3, okay? So we'll go ahead and keep writing limit, and we're going to have t minus 1 to the 1/3 minus, I'll keep that 3 on the outside, 0 minus 1 to the 1/3, okay? Plus the limit as t approaches 1 from the right, keep that 3 on the outside, and we have 3 minus 1 to the 1/3 minus t minus 1 to the 1/3. And you can't cancel these out because the t is approaching a different, from a different direction. So make sure you get that. Okay, let's have a cleanup line. T approaches 1 from the left. And as you can see right here, this is a negative 1 to the 1/3 power, which is going to be a negative 1. Okay, so we're going to have 3 times t minus 1 to the 1/3 power, and this is a minus a negative 1 plus, I probably could have skipped this line and just gone to the next, but I think it's nice to have this 2 to the 1/3 power minus t minus 1 to the 1/3, okay? So this would have been a plus 1 there, okay? So let's go ahead and plug 1 in. And remember, we're coming from the left, so we're slightly less than 1, okay? So we have 3 times 0 minus a negative 1 is a plus 1, plus 3 times 2 to the 1/3 minus 0. Pretty cool. So that's equal to 3 plus 3 cube roots of 2. Therefore, our integral converges. Okay? So I was trying to think if there was something that I wanted to say about this. Oh, if we would have waited on this and just come all the way down here and gotten 3, we knew we would have had to go then work on this integral. Because if this was convergent, then the whole integral converged. But if this would have been divergent, then the whole integral would have diverged. Okay? So both pieces, both integrals must be convergent in order for the given integral to be convergent. And